Okay, we will start now. So today we will deal with the thermal stress. As I said in the last class, like actually it was supposed to be taught in the last class, but still, like because of time constraint, I couldn't complete it. I couldn't start it. Okay. So in the last class we talked about this other more elastic constants like shear modulus, bulk modulus, along with this elastic modulus. Then we also dealt a question with like how to find the elongation in bars with varying cross-sectional area. So bars with varying cross-sectional area is an example for a composite bar. We will deal with another type of composite bars today. I mean within a different pattern, and also we will talk about thermal stress. So what is a composite bar actually? So bars made up of two or more materials are called this composite bar or compound bars, and they may have same length or different length. And our question is, when we are given with such a bar, how to find the elongation of the composite bar which is subjected to axial loads. For example, in this figure, so left side this is a material 1 and the right side the material 2, it is having common length, like, and it is subjected to axial load P. So if you take a cross section, for example, like I just take a cross section here, the net force acting at this cross section on these two will be the total load P, because it is subjected to a load P here. But at the same time, the force developed in the material, okay, the force developed in each material will be different. We call it as let it be P1 and P2. So we will get this equation using the equilibrium of forces, that the total force P will be P1 plus P2. But at the same time, there is a compatibility condition. We are keeping these edges as restrained, like they cannot elongate. So what happens? Or no, sir, not elongating. Like we are saying that these two are jointly kept together. So what happens? Like if this material elongates, the same quantity this material also has to elongate. So we apply a compatibility condition here, saying that delta 1 is the elongation in the material 1, delta 2 is the elongation in the material 2. So what happens is that both these elongations are same. And then we know what is delta. Delta is nothing but PL by AE. And using that information, we can write, we will get this expression where we are equating both the different elongations in both the bars. So in the last class, we considered a body something like this, a bar with varying cross-sectional area. Yeah. So this has length L1, E1, maybe the cross-sectional area, let it be A1. It has L2, E2, A2. I am applying a tensile force. Okay. So now if you take any cross-section, say let it be the cross-section in the first material, another cross-section in the second material, we can see that the tensile force is acting common. And yeah, this tensile load P is acting common in both the materials. So, but there will be an elongation for this material, and there will be another elongation for the second material. So, effectively, what happens is the total elongation will be delta 1 plus delta 2, and we are getting delta 1 as P1 L1 by A1 E1. This is the expression. So in the last class, I just assumed that E1 equal to E2 equal to E. So and here P1 and P2 equal to same, equal to P. So it will be P by E, L1 by A1 plus L2 by A2, like that. So I hope you understood the difference between the two problems. The first one, the material, both the materials are fixed together, but at the same time the elongation is same in both the cases. I mean, from both the materials. But here, the one is attached to the other one. So the elongation we have to consider like elongation from the first material plus the elongation from the second material. That's how we can calculate the total elongation. Now we will have a numerical example. A compound bar of length 600 mm consists of a strip of aluminium 40 mm wide and 20 mm thick, and a strip of steel 60 mm wide by 50 mm thick, and they are rigidly joined at the ends. The elastic modulus of aluminium and steel are given here. Determine the stress developed in each material. This is 10 raised to 5. When axial tensile forces 60 kN acts. Okay, I will give you 5 minutes. Meanwhile, I will call one name. Nasir, are you here now?
So yes, sir, I'm present.
Okay, so you can start solving this problem. So Nasir, can you give some update?
Yes, sir. Stress is equal to force by area. So we can find stress.
Hmm. Okay. If you can tell me some steps, I can write here also. So others will also give
Okay.
some help.
Okay, sir. So the given force is 60 kilonewton, sir.
Okay. Thank you, sir.
And the area we can use pi r square, cross sectional area.
Okay.
Can I see the question, sir?
Yeah, sure.
Okay, so first we can calculate for uh, steel, sir. Stress. We can calculate stress developed for steel.
Okay.
So we can use the above formula pi r square 16 to 10 power 3 by pi into.
I will write here then. Okay.
So
No, like in the this previous case, I mentioned like, see, there are two forces here,
yes, sir.
P1 and P2. Okay.
Yes, sir.
So I'm just taking a cross section here.
Yes, sir.
So in each material there will be two loads. Let it be say one. Let it be which are the materials? Aluminum. Okay. PA.
Yes, sir.
The other one is steel. PS.
Okay, sir.
And that is equal to P. P, which is nothing but 60 kilonewton.
Yes, sir.
And now what is the deflection associated with this aluminum, and what is the deflection associated with the steel?
So deflection, you mean by change in length?
Yeah, not change in length, the elongation. That's what I meant.
Elongation. Okay.
So what will be the
So we
elongation?
can use PL by AE, sir.
PL by AE.
Yes, sir.
So the deflection in steel will be
For steel, yes, sir.
PS LS by AE. Okay.
Yes.
But at the same time, L is a common part, so I will just put
600. Yes,
L only.
L.
And the strain
Plus
in
for
aluminium will be similarly
same. So
PA.
PL, PAL by A. A.
Okay.
E is also. Oh, E is different. Okay, sir.
And they are rigidly joined here.
Yes, sir.
So what happens? What you can say
So
about
delta
delta S and
S is
delta
equal
L?
to delta X.
Yes.
Both are equal.
Okay. And when you equate these two equations, what will you get? So you will get so what are the unknown quantities here in this expression and this
E
expression?
is known. A only. Sir, AS by A we can get, sir.
Hmm.
PS we
AS,
can substitute. Yes, sir. E is known, sir, for both.
yes.
L will get cancelled and ratio of the area we can find, sir. AS by AA.
What about PS and PA?
So that we can substitute from this equation. So BA plus PS is equal to 60.
Okay. So you are saying you will use this equation, and which is the next equation you are using? This is the one equation you are using.
We can take PA is equal to 60 minus PS and substitute that in this.
This expression, right?
Yes, sir.
Okay.
Yes, sir.
Because here there are two unknowns, PS and PA, and
Yes.
you are applying the equilibrium equation first, and then you are applying the compatibility equation.
Yes, sir.
Okay. And so now we are getting so when you apply this previous equation, from this you will get as PS is equal to something like around 2.25 PA. Okay. And when you substitute this into this part, you will get yes. So someone, okay. So can someone try to solve what? Did you get any, like someone solve this problem? Did you get the final answers?
Sir, the answers are 41.53 and 18.46, sir.
Okay. Can you tell your name?
Sharan, sir.
Yeah. So what is the value for PA? Which is 41 and which is 18?
So 1 second, sir. I will just.
PS is 41.538.
Sir, steel is 41. Steel is 18.46, sir, and aluminium. The other one is 41.5. Aluminium, yes.
Aluminum, I think aluminum is 18 point. Check again. Aluminum is 18.462, right?
Yes, sir. Aluminium is 18.46.
Aluminum is 18.462, sir.
Oh, okay. And steel is 41.538.
30.
Yes, sir.
And there is one more part of this question. No, actually, determine the stresses developed in each material. So we just found what is PS and PE. So we need to find the stresses. Sigma A and sigma S. So I will call another name. Manoj, are you here? Manoj? What about Jacob Thomas? I think yesterday he was not here. Manoj and Jacob Thomas. Okay, you'll be given absent for today's class. What about Vinith? Vinith, are you here? Vinith Karthik Raja. Again absent for today's class. Sridharan.
Yes, sir. Hello.
Yeah. So I need to find what is the sigma A and sigma S here.
Yes, sir. We will be dividing that by the area, sir. Area, sir.
Okay, so can you tell me the answer?
So, question once again, sir, please.
Yeah, sure. You just need to say what is the area of aluminium, what is the area of steel. It's not a big deal.
Sir, area is 40 mm into 20 mm. Sir.
Okay. And you need to calculate the, yeah. Other one is 60 mm by 50 mm. So what will be the, what will be the stress developed in aluminium?
0.023.
Unit.
Unit is Newton per mm square. Sir.
0.023.
Newton per mm square.
How did you get that?
Sir, 18.462. Sir, kilonewton. Okay, so it's in kilonewton.
Yeah, exactly, kilonewton. And what will be the value for steel?
Steel, just a moment, sir. Question, sir.
Sure.
Sir, it is 0.046 kilonewton per mm square, sir.
Okay, so it is 46.15 Newton per millimeter square.
Yes, sir.
This Newton per millimeter square or MPa, this is the common term which we use in our like almost all design. So when you are reporting these values, either say in Newton per millimeter square or MPa or otherwise gigapascal, MPa, like that. Okay. When you are mentioning when you are telling about force, either you can say about Newton or kilonewton, like that. And what will be the elongation? That extension of the compound bar when axial tensile force of 60 kilonewton acts. Basically, you need to find this expression, one of these expression that I am leaving to you. I hope you can finish it. Right? Can someone tell the answer?
So is it 65?
65 unit.
Um,
No, it's not 65.
Sir, 0.138 millimeter.
Yes, that is 0.138 millimeter. You just need to put these values back into this equation. Any one of this equation, either this or this, because we are assuming delta S is equal to delta A. Okay, now we'll move to thermal stress today. So, when a material undergoes a change in temperature, like two things can happen. Like the change in temperature can be like increase in temperature or decrease in the temperature. So when temperature increases, the material has a tendency to elongate. Okay, and similarly, like when temperature decreases, the material can contract also. Suppose this is our body, this is the bar, and if there is a temperature increase is happening, then this body elongates like this. So this elongation, this part is called, this is the elongated length delta. And
so your voice is breaking.
Okay, 1 second again. Can you hear me now? Hello?
Yes, sir.
Yeah. So if the elongation of or contraction is not restricted, that is free, then the material does not experience any stress, but it undergoes only a strain. So I'm just giving two figures here. Here, one side it is restrained, and another side it is not restrained. It is a free end here. But here, both the ends are restrained, like they are fixed in both the parts. So what happens is like here in this case, if I apply a temperature, then it undergoes a strain, but there is no stress developed here because this part it is free to elongate. But in this case, there will be a stress developed in both the area. Like stress will be developed in the support, and we call it as the stress developed is called the thermal stress. Okay, the free expansion or contraction of materials when restrained induces some stress in the material known as the thermal stress. So you should ask me a question like if I am applying a temperature here, why don't thermal stress develop in this region? If you apply a temperature change, this portion also will experience a thermal stress. But for our calculation easiness, we will assume that the elongation is happening in one direction only. But in practice, this material elongates in both the directions. Okay, this is just for calculation purpose. So from many experimental studies, it can be shown that this thermal strain is proportional to the temperature change. So what is thermal strain here? Thermal strain is nothing but this change in length due to the temperature effect divided by the original length. And we are saying that this thermal strain is proportional to change in temperature, and this proportionality can be changed by putting a constant. That constant is known as coefficient of thermal expansion, and this is the property of a material. So can someone tell me like what will be the unit of alpha?
Sir, meter inverse.
Can you tell the name?
Temperature inverse, sir. Sorry, temperature inverse.
Temperature
Yeah.
inverse.
Temperature inverse. Because strain is not having any unit, delta T having a temperature of temperature unit. So alpha will have the reciprocal of the temperature unit. So either we will say it is the Kelvin or sometimes it is called like degree Celsius inverse or Kelvin inverse, like that. At this moment, I want to tell you a thing. Can you tell me the difference between small capital K normal, small k normal, and small k italic, capital K italic. Yeah, anyone can answer this.
So capital K is Kelvin
So what is
and small k is Boltzmann constant.
Oh, okay.
Then the slant k is I think bulk modulus.
Okay. Yeah. Yeah. What you have said is correct. We can. Okay. What I expected was like K for capital K is for Kelvin. Okay. And when you write small k, like usually we give the small k for kilonewton, kilogram, like that. So when you write kilonewton, you should not never write capital K and capital N. It means like you are multiplying temperature into Newton. You should always write small k and with a capital N. And this italic k is again like when you see any textbooks, these people uses italic k, like the load is given as an italic, like sorry, this one on this one. Italic ways. So this in italic is actually for noting some any variables. So this in dynamics it can be like a stiffness. The the stiffness associated with a beam, it is denoted by capital K with the italic version. So this one you have to be particularly noted, like when you write kilonewton, you should never write capital K and Newton. You should write small k and Newton, and the units are never written in italic form. They are always in the regular form without italic. So the thermal stress produces the same effect in the material similar to that of a mechanical stress. So what happens, like with increase in temperature, a compressive stress is developed in the material. So I will show you here. So this is our bar, and we are restricting the supports, both the supports. Now I apply a delta T, that to positive, like increase in temperature. So what happens? There is a elongation happening. This both part tries to elongate. But what is it? But both the supports are restricting that elongation. So what happens ineffectively? There is a compressive force acting from these supports, which makes this elongation to be suppressed. So that's why with the increase in temperature, there is a compressive stress is developed. Similarly, the opposite. When a decrease in temperature, a stress developed will be the tensile stress. Like when it decrease in temperature, there will be decrease in there is a shortening of the bar. But at the supports, it tries to pull back to the original shape. So that developed stress will be the tensile nature. And similarly, we have the expression for tensile stress. The thermal stress. Thermal stress, we are having sigma T equal to E into epsilon from the Hooke's law, and epsilon we are writing as alpha into delta T, where alpha is the coefficient of thermal expansion, delta T is the change in temperature. The unit of thermal stress, everything will be same, Newton per millimeter square. All that part remain unchanged from the last sections. Now we'll go to this case, but like okay, this is the one which I explained a little while before. So if free expansion is like, if there is no support, like this support is not there, then it will have a elongation. This elongation is nothing but L into alpha T. Alpha T is nothing but the change in length by the original length. So this delta will be L into alpha T. So this is delta. But the support is not permitting the elongation. So what happens? The body, this delta has to be like it will be restricted back. So the body will be in the original shape. So there will be a load there is a compressive load acting here, and we need to find what is this compressive load. So most of the questions are like we need to find what will be the compressive force or compressive stress developed as a result of the thermal expansion. So we know that this is an example for a axially loaded bar, and if P is the load acting there, L is the length, A is the cross-sectional area, E is the modulus of elasticity, then we can say we know that PL by AE is the expression for the deflection, and we just equate that deflection to the deflection which occurs due to the thermal expansion, and we can write from this, we can get the expression for P is nothing but AE alpha delta T, and the expression for stress will be P by A, which is nothing but E alpha delta T. Okay. Now the another case. Anyone has any doubts?
Sir, if it is restricted, we don't have the expansion, no, sir. So how are we using these equations?
Yeah, if it is restricted, there is no expansion. But what happens actually, if it is not restricted, it will elongate. See, this is a there is no other external force acting on this figure right now. Okay, but we are applying a temperature. Some delta T temperature is applied. As a result, it tries to expand. But what happens is like there is a support at this end. So this support actually tries to stop this elongation, this delta. So how can it stop without? How can it stop? The support has to internally provide some resistive force, which is the P here. So this P will be internally developed by the support, and it applies on the bar.
So it's a reaction force that is stopping the elongation. So
yes,
we
exactly.
use the equation.
Yes, it is a reaction which is developed at the supports, which prevents this elongation delta due to the delta T, like the change in temperature.
Okay, sir.
Okay. And similarly, if the expansion is prevented partially, like we are having a bar which is having a length L, but there is a gap here, which is measured by the small letter delta. So because of this, we are assuming there is a expansion because of delta T change in temperature, and this is the delta which is because of the change in temperature. So this delta is nothing but L alpha delta T. Okay. L alpha delta T. But this expansion is prevented. Like delta is a gap, so this is allowed. This portion is allowed, but the second portion, this portion is not allowed there. This expansion will be prevented, and so the net delta change in length will be L alpha delta T minus delta. Sorry. So what will be the force here? Suppose the internal reaction is P. The internal reaction is P here. Then how can we calculate? What can we say about this P here? Someone can answer that.
Sir, we can replace P. We can equate PL by AE is equal to this delta L alpha delta T minus del.
Yes, exactly. This delta equal to L alpha delta T minus delta, and from this we can find what is P, what is a sigma T, etc. Yeah, so based on this idea, like I'm putting a problem. A steel rail is 12 meter long and is laid at temperature of 18 degrees Celsius. Maximum temperature expected is 40 degrees Celsius. estimate the minimum gap between two rails to be left so that temperature stresses do not develop. Similarly, the calculated temperatures. Okay, so I will call one name. Satyajit Patil. Yesterday also, and I called him, he was not there initially, and then he came in between. Satyajit Patil, are you here? So by any chance Manoj is back? Or Jacob Thomas? Vinny. Okay. So, who is this now?
Me.
Okay. You already got your attendance today. So, can you solve this question?
Yes, I'm solving. Okay. L alpha delta T till 18 degrees Celsius delta T it's 14 22 solid.
I can also help you. Just start with some.
I've started, sir. First question. I'm trying first question, sir.
Yeah.
I'm trying to find the strain, sir, so that I'll find the stress.
Okay.
I'll find the gap. 12 into 10 power minus 6. 22.
The question, sir.
Yeah. One second. Just a second.
Sir, one doubt, sir. Sir, one doubt.
Sir,
Yeah.
question, sir.
Yeah. Just a second. Give me a second. Yeah. Back. I think some noise.
Tom, turn off your mic.
So first we have to find the strains delta. Sorry, the expansion, sir.
Okay.
In the between the given temperatures, that is between 40 and 18. The delta T will be 22 degrees Celsius, sir.
Delta T is 22. Okay.
With that, we'll find the maximum expansion, sir.
So what is the expression for that?
Delta equal to L alpha delta T.
L alpha delta T. Now, how much you are getting this one?
It will be 3.168 into 10 power minus 3, sir.
Unit. When you report some values, just tell me the unit also.
It will be in meters, sir. It will be in meters. So if we convert it to millimeters, it will be 3.168 millimeters, sir.
Yes. Okay.
So the two rails will be there, right, sir? So I think we have to give a half of the. This will be the minimum gap between the two rails, sir.
Yeah, so we should provide at least a minimum gap of 3.168 millimeter. Otherwise, the stresses will develop.
Yes, sir.
Yeah, I think you almost have seen, like in bridges, ducts, and all. Like there is a small gap. Like when you try to like drive a car through the bridge, you will see some sort of a irregularity, bump sound. Have you noticed that?
Yes, sir.
So the reason why we are giving this because of the temperature from the sun. Like in some climate, there is a chance that the tar or the bridge, like the material, it can expand. So if we are not giving a gap there, then the thermal stress will develop. So in order to avoid this thermal stress, we are giving a gap. We are deliberately giving a gap on the tar along the bridge.
Okay, sir.
So that's why when you move the car over these gaps, like you can feel it when the tires move over these gaps. So the second question I will give to Harish Kumar. Harish Kumar, are you here?
Hello, so can you hear me?
Yeah, I can hear you.
So can you hear me?
Yes, I can hear you.
Okay, so second is the calculate the temperature stresses, right?
Yes.
For no expansions, the formula to be used is delta equals PL by AE, which is delta we found as 3.16. And we equate it to PL by AE, and the B part we need to use the sigma part, so 3.16 minus 1.5 for the B part.
For the first part, can you calculate the temperature stress?
Yes, sir, I'll do and I'll tell you.
Kirti wasn't be ready with the third part of the question. So can you put the values, Harish?
Yes, so once again, so it's doing it 3.16 into. Hello.
Into, yeah.
Into 2 into 10 power 5.
5. Then. Yeah. After this. No, what you have to do here? Can you tell me what you are planning to do? Hello. So we need to find temperature stress here. So temperature stress is nothing but this expression P by A. We call it as sigma T. So sigma T is nothing but, now we can see that it will be delta E by L. Delta we already calculated from the last step. E is 2 into 10 to the power of 5 by L. L is
12, sir.
Yeah, L is 12 meter.
Yes, sir.
So how much is the value you are getting?
Once again, sir. Sir, 52.8.
Unit.
Unit will be one second, sir.
What is the unit for 3.168?
Mm.
Okay. Denominator unit.
Denominator is, so that's in meters. No. So denominator is also in mm.
And what is the unit for 2 into 10 raised to 5?
So yeah, Newton per meter square. Newton per millimeter square.
The final unit is
Newton per millimeter.
Newton per millimeter.
No. Newton per millimeter square.
Okay.
Yeah, Newton per millimeter square.
Yeah, so the next person. No. Harish is the second part. If 1.5
So,
mm gap is provided.
So we can just subtract 3.16 with 1.5.
Okay.
We get 1.668.
1.668. Okay, and tell me the stress.
Stress. Stress is P by A, which is P by A we have as
okay, you just need to put 3.168 minus 1.5.
That's for the B part, sir.
Yeah, and from that you can find what is B by A, which is the sigma stress, sigma T, thermal stress. Okay.
Okay.
So Kirti, okay, thank you, Harish. And the next one, Kirti Vasan. Kirti Vasan, are you here? Kirti Vasan, I think absent for today's class. Kandesh Kumar, roll number 49.
Sir, he is also absent, sir.
Pardon?
He is also not there, sir. I think he is also absent.
Oh, okay. Google.
Sir?
Yeah, so can you solve the third part?
Sir?
The third part is the stress delta is 20 Newton per millimeter square. What is the gap provided between the rays? I'm running out of time.
Sir, stress into length into 10 power. Sir?
Yeah.
Sir, can you hear me?
Yeah, I can hear you. Who is it?
Sir. Gokul, sir, Gokul.
Google, okay, yeah.
Sir, 20 stress 20 into 12 by 2 into 10 power 2.
It will be better if you can start with the expression, so others will also find it easy.
So stress into L by E is equal to the gap delta.
How did you get this expression?
So change in the gap.
So this is our expression. You are given with the stress. Stress is nothing but P by A. You know what is L, what is E, and you know this quantity, the free expansion away, and you need to find what is delta.
E.
Okay.
Yes, sir.
Are you understanding this theory, or just are you feeling any trouble?
No, sir. Understanding, sir.
Okay. So this is wrong. You need to. Yeah. Tell me.
What is the answer, sir?
So can you put? So you tell me the answer. I will tell whether it is correct or not.
Is it 1.968?
Yeah. Unit is
Yes,
in
sir.
mm. Okay.
1.968 mm.
Yes. 1.968 mm.
Okay, sir.
Okay. This will be the final problem for today's class.
Sir, in the previous question, why we are taking temperature in Kelvin? We are taking degrees Celsius only. Why? Why we are not taking Kelvin?
We can take. No, I didn't get your question. Are you asking me why we are not taking in Kelvin? Why we are taking in degree Celsius?
Yes, sir.
Because the information provided, no, the alpha, the unit is in degree Celsius. I mean reciprocal degree Celsius inverse. So that's why here also degree Celsius. You can convert to Kelvin. At the same time, you need to convert the unit of alpha also to Kelvin.
Okay.
Okay. And this will be the last question for today's class. A composite bar is rigidly fixed at the ends A and B. Determine the reaction developed at the ends when temperature is raised by 18 degrees Celsius. So whom should I call? Roll number 89, Rishi Viranjan. Are you here?
Yes, sir. I will. Yes, sir. Yes, I can hear.
Yeah. So can you solve this problem? Like we can do it together. So can you start with it?
So delta T is given 18 degrees Celsius. EA equals to D alpha D. Another reaction developed. So we can take PL by A equals to delta L. No.
Can you repeat? I couldn't hear it properly. Can you repeat it?
Just once I said we can take PL by AE, but no, it's we have to find the reaction developed at the end when the temperature.
Okay, so what happens if we increase the temperature in this bar? There is aluminum and there is a steel. So these two quantities tries to expand. So it goes like this, and here also it goes like this. But there is an issue that there is a support at both the ends which tries to bring back this elongation into the original, like the total net elongation will be 0. So how can we calculate this delta? Let it be delta A. Let it be delta. Yes.
So we know the tensile load is equals to sigma A.
Sigma into A. Okay, that is some sort of expression for load.
Sir, your voice is not audible.
Yeah, I got your point. Like sigma, P equal to sigma into A.
Yes, sir. So we can equate both sigmas for each other.
No.
PL by AE equals to delta L. Determine the reaction developed at the
Okay, I will give you one more clue. So we are having two members. Okay, and due to the effect of the 1 second, do you have class from 1:30 onwards?
no, sir.
I will take 5 more minutes. That's all. Okay. So you have two members. One is aluminium, one is steel, and because of this change in temperature, increase in temperature, it tries to elongate.
Yes.
But what happens is like there is a support at both the ends, and as a result, this elongation is not actually happening. So what is
Yes.
happening at the support? There is a reaction developed at the support.
Yes, sir.
What can you say about this reaction? This reaction will be equal. Right.
Yes, sir.
Now, tell me. Now you can think about the this case. You can start with some equations. And okay, again, can you tell me like what will be the elongation because of the in aluminium because of the change in temperature, delta A?
So 11 into 10 to the power minus 6. So we can do one thing. We can P into L is length is given as 1.5 plus 3. Whole no. For aluminum we can find length is 1. P into 1.5 upon area is given 600 meters square into E is given as 70, which is equals to delta L. And delta L is
Can you tell me the expression again? In expression
P
form, can you
into,
tell me?
yes, sir. We know that P into length by area into Young's modulus is equals to alpha delta T
Alpha delta T.
equals to
Okay.
alpha delta T. So P we need to find. Length is given for aluminum as 1.5. Area is given 600. And Young's modulus is given as 70 into 10 to the power 3 equals to delta L we can find by alpha delta T. Alpha is we know as 11 into 10 to the power minus 6 and delta T is 18.
So that is for aluminum you are saying.
Yes, sir.
And what about the steel? So you are saying like PL by AE, that is for aluminum.
Yes, sir.
So L for aluminium, A for aluminium, E for aluminium. There is a PA. Then alpha for aluminium, delta T is common here.
Yes, sir.
And what about for the steel?
So steel
So
is
sir,
also
it will be L alpha delta T, sir.
I didn't hear you. Can you repeat?
L alpha delta T, sir.
This will be L alpha delta T.
Yes, sir.
Yes. So L is again for aluminum. Yes. Right. Yeah. So tell me the answer then. So you are saying like then for similarly for steel there will be PS LS by AS ES equal to LS alpha S delta T. This is what you are trying to say, right?
Yes, sir.
But still, how can you calculate PA and PS here from this expression?
Sir, if we will equate.
No, we cannot equate anything. Okay, I will tell it now. In the previous case, so as I said, there will be, when we apply a temperature, there will increase in temperature, there will be an elongation in the aluminum part, which is represented by delta A here, and there will be an elongation in the steel part. So we can calculate what is delta A and delta S. How? Like alpha A into length into delta T. Length for this aluminum part into delta T.
Okay, sir.
So the now the, so this is wrong. This is wrong. So the total elongation will be nothing but delta equal to delta A plus delta S. Okay. But what happens is, like, because of this delta increase in this increase in the, what do we say? Yeah, because of this increase in the elongation in the aluminum, we can write separately this delta A as nothing but PL by AE, sorry, LA by EA, and this also PLS by AS ES. Okay, and you know what is delta here? Delta, because we are calculating this quantity alpha A L into alpha A LA alpha T. Okay, I will write the expression for delta. Delta A will be alpha A LA delta T plus alpha steel, length of steel plus delta T. So you know what is coefficient of thermal expansion for aluminum and steel? It is given in the problem. Length also is given in the diagram. Delta T, you know. So you can find what is the total elongation happening because of the change in temperature. And now we are saying that this elongation in the steel, you can write this expression PL by AE. Is that okay?
Yes, sir.
Hello.
Yes, sir. Yes.
And similarly for the steel part, again we have having, because for in general we know that change in length will be PL by AE. So in this quantity, the unknown quantity in this expression, the unknown quantity is P. The P is the force which is the the reaction developed at the supports. Are you clear with it?
Yes, sir.
Maybe I will try to explain one
Sir,
more time.
sir, just want to ask that whether the reaction forces of both will be same or the stresses developed will be same.
The tensile forces will be same.
Stresses will be different because they are having different cross section area.
Yes, the stresses will be different because when you take a cross section here, so here the stress will be calculated as P upon area of this cross section, that is aluminum. And at this point, this is sigma A. And at this area, the stresses will be different. Like sigma steel will be the load by AS. AS, yeah.
Yes, sir. Yes, sir. I got it.
So basically, what happens is, like, because of the elongation, there is a tensile force back in developed there. No, not tensile force. It's a compressive force developed in this bar, and this bar is like in the effect of a compression. So, and this expression you have studied in the previous, like, not the, like from the last lectures, like if a bar is subjected to a compressive load, then the shortening of the bar is given by this expression PL by AE, and we are equating this expression to the shortening due to the thermal effect. That's what we are doing here. Okay. I need to download that. Yeah.
Sir, we are taking two materials like aluminum and steel of totally different dimensions. While the P cannot be different, we are taking the P will same only from both the directions.
P is same in the both the direction. So when you take a cross section like this, so what will be the force at this cross section?
It will be in against P, means that back direction. Resisting direction.
Resisting direction. No, I'm saying like in this cross section also the force acting at that cross section will be same. At aluminium also it will be P, and at the steel also it will be P. But as you said, there is a material property. The material property is associated with this, like it depends upon the cross-sectional area there. So the stress developed in the aluminium and steel will be different. Sigma A and sigma S will be different, but the force acting at this cross-section will be same. And maybe I will put another figure. Suppose if aluminium and steel is kept like this. This is aluminium, this is steel. Then the situation will be different. There is the force acting, then if it is subjected to P, then there is a, we can say the load developed in the aluminium is P1, PA, the load developed in the steel is PS, then it is actually equal to P. But for here, PA equal to PS equal to P. Because when you see the cross section, at that cross section, the common load is acting, like the P is acting, the full P is acting at this cross section. But here, when you take a cross section, some part of P is acting at this cross section, and some part of this P is acting at this cross section of the steel. So ineffectively, the P can be, in this case, the P can be written as PA plus PS, but here, PA equal to PS equal to P.
So what if both loads are vertical?
What if both loads are?
Sir, if both the loads are vertical, like aluminum and then after steel, at the time the reaction force will be equal to weight of the steel or weight of aluminum plus steel.
Yeah, till now we are considering only axially loaded bar. Okay, axially loaded bar. So we are considering only the forces which are acting along the axis, and we are neglecting the weight of this aluminum and steel in this problem. But when it comes to, if you are considering, then the problem will change. Now we have to treat this problem as a beam, which we are going to study in this course also, where there will be like a vertical force and vertical reaction developed at the supports. But this one, so starting, just we are considering only the axially loaded bar, so there will be like axial forces are developed at the supports.
Okay, sir.
Anyway, I think the module 2 is about these beams, and we are going to deal that also in this semester.
Okay, sir. Thank you, sir.
Anyone has any doubts?